fresh graduate student, and also Dr. Chen. So when we're talking about fractional order flight control, we need to provide some motivation, say like why we want to introduce fractional order control to the UAVs. For UAV, I mean just unmanned aero vehicle. Yeah, you can see for the figure below. Oh yeah, this one is just a platform developed here in CSOS, which is totally open source. I mean, we have all the code, all the hardware, all the software. Yeah, we can add cameras to it to fly for every image acquisition. Say like we can use that information to do a lot of things like irrigation control, and also say like if we want to monitor a chemical leaking problem, say we can send out a bunch of UAVs just to take pictures of the whole field. Yeah, and then we can know, yeah, say like where the diffusion is, you know, how the diffusion evolves. Yeah, this kind of stuff. Yeah, and we all know that these small UAVs draws a lot of interest around the world, especially say like within 5 years, just because the electrical devices are becoming smaller and smaller, and we can use it as pretty cheap. See, like the platform, this one is the price is below 5 grand. So, and but another challenge for doing this kind of unmanned flight is since this kind of aircraft is not so strictly, I mean, a lot of standard, industry standard like manned aircraft, because manned aircraft, there are human lives involved, so it's pretty critical and it's dual considerations. So say like if this engine fails, there's another one, but for unmanned air vehicles, you don't need to worry about that, so it's just pretty cheap solution, and it's, you can say it's not expensive sensors. For this one, we are using some inertial navigation units, and all these bodies are made by ourselves, which, you know, introduce a lot of uncertainty. So here we kind of want to introduce a fractional order control to the, you know, not so well modeled system. Say like trying to see, you know, if we have some, you know, we assume we don't know the accurate model of the system, can we control the plane well? This kind of stuff. And also another thing is like we know the memories are becoming cheaper and cheaper, you know, and but you know our controller is kind of pretty simple. Say like the most frequently used controller is this PID controllers. Actually, we just use the first derivative and the simple integral. You know, that's integer order PID. That's pretty classical methods. And due to one reference is saying like in chemical industrial, more than 90% of the controllers still using this PID. But we can obviously see here, because this controller just use the first derivative. You know, all the other data are lost. We are not using it. We just use the current data and the data which is one time step ahead. So that means the controller is kind of, you know, not so sophisticated and not so, you know, wise. So, but for fractional order, we kind of introduce this fractional order derivative and fractional order integral to it, so that, you know, introduce a lot of memory to it. And also we can see the advantage of fractional order control is, say like given an integer order control, we can see it's not so easy to control the phase. But for fractional order controller, due to the lambda here, it's variable, so we can kind of got more flexibilities. Just for this paper, I just give an example of a fractional PI instead of this PID, just for a fair comparison, because for this one we got 3 parameters, K, PK, and KD, but for this one we also got 3 K, PK, and lambda. So it's make a fair comparison. Just if we want to control design a fractional order controller, we kind of need to determine all these 3 parameters. So we have a bunch of some requirements. Of course, just we require the phase margin, crossover frequency. This just all for stability, and also for the robustness. We ask this phase angle to be flat. Close to cutoff frequencies that can introduce a lot of robustness. But given these 3 requirements, we cannot. It's not all the time. We cannot always find the solution for integer order PID control. But for fractional order PID control, we can always find the solution. So that's an advantage we have. So based on that, I throw it into a 6-degree freedom MATLAB model to test it first. This one is just a Similic model, developed by some researchers, working on that NASA UAV Aerosonde. Is a fairly mid-size UAV, and but the control surface and these things are pretty similar. So I just use this one here to simulate my result. So to make comparison, I did some comparison. Here is just some the x-axis is just time, the y-axis is row angle. The row angle basically means turn left or turn right. Here I give a command say 10 degree, turn left 10 degrees. So if we wanted to turn left 10 degrees, we don't want this overshoots. We just wanted to go to 10 degrees as quick as possible. At the same time, not so much overshoot. So we can see here, if the open loop, there are a lot of overshoot. But for comparison, we have a classical, modified Ziegler-Nickers tuning rule, which can generate Kp, Ki, Kd, and we can see here this modified Ziegler-Nickers can go not so fast as fractional order controller. A more advantage can be shown later in this figure. For this one, we are trying to simulate a wind gust. When we are flying unmanned air vehicles, it's going to be a changing world. It's not going to be that stable. So here we are trying to simulate the circumstance that, say, assume at 5 we got a wind gust. Say, assume there's no wind before 5. At 5, we got a wind, say, last for, I remember it's a quarter the second, I think. No, probably 4 seconds. So here I just assume there's a strong wind all of a sudden to see how the controller performs. So we can see here clearly, fractional order controller can come back pretty quick, while the integer order have some little delay. Of course, we cannot, oh yeah, there should be another figure showing, the fractional order control outperforms the integer order while it's we can change the payloads. They assume the payload is a little different. Anyway, in conclusion, we just try our focus to implement these fractional order controllers on UAVs, and but for realization of fractional order control, it's not so simple as doing theoretical approach, because we have to do high order approximations, and here is some kind of challenge, and how to make this one simple and easier for industrial engineers is just a problem we going to focus. Yeah, that's all. Thanks.
Good. Thank you.